Hello, everyone. My name is Shay Moran, and I will present a joint work with Noga, Alon, Hanneke, and Holzman about the theory of back learnability of partial concept classes. Okay, so the starting point of this project is the fact that the traditional ML theory and statistics, in particular back learning, do not explain generalization in modern algorithms. This is most notable in neural networks, but not only. It has also been observed in other algorithms. In a nutshell, the reason is because the traditional theory is based on a worst-case perspective, a perspective that reduces generalization or learning to empirical risk minimization over restricted classes. And this is in contrast with modern algorithms that use huge hypotheses with many parameters, and this dichotomy, really poses exciting and interesting research questions for theoreticians. And the approach we take in this project is to revisit the axioms, the very basic definitions of learnability, and in a way that circumvents the traditional worst-case perspective and is better suited to capture good or nice properties of the input of the data. Yeah, so let's see, what do I mean by that? So the motivation is that in practical problems, the data often satisfies special properties that ease learning. So one example is that the data, despite being high dimensional as encoded by the computer, it actually lies on a low dimensional surface. So you can imagine images, for instance. Another popular example is linear classification with margin. So again, the data might be very high dimensional, but it satisfies some margin assumption. So the data is not too close to the decision boundary. And there are many other examples. So the idea is really simple. In order to capture such scenarios, we extend the classical learning theory by considering partial concepts. These are simply functions that can be undefined on part of the space. So formally, a total concept is a function from the domain to the label space, to 0 and 1. And the partial concept is a partial function. So there is another label, which we call star, which reflects the fact that the function is not defined where it is equal to star. Okay, so the support of a partial concept is simply the set of all points where it is not equal to star. Great. Now notice that with this simple modification, it is very easy to express data-dependent assumptions. So let's consider the previous examples. So linear classification with margin, we simply take a partial concept which is undefined near the decision boundary. Similarly, if we have data that lies on low-dimensional surface, we take a partial concept that is only defined on the surface and is undefined everywhere else. At the same time, the basic learning theoretic definitions extend in a very natural and obvious way to partial concepts. So let's just consider a few, for example. So first of all, the error of a classifier is defined exactly in the same way. So so we only consider distributions P over true examples. So the distributions always produce examples whose labels are 0 and 1. So there is never a star. And the error of a classifier is simply the probability that it misclassifies an example drawn from the distribution. Notice that this definition implies that in our algorithms, we can just always output total concepts, because if we output a star, if we output a partial concept, then this partial concept will always be wrong, where it is equal to star. Okay, so also a very important definition in learning theory is of realizability. So consider a class of partial concepts. A distribution P over examples is realizable by the class if every sample from it is realizable by the class, right? So if with probability 1, when we take a sample from the distribution, it will be realizable by the class. Now, what does it mean that a sample is realizable by the class? It means that there exists a partial concept in the class that labels all the examples in the sample correctly. And now, once we have the definition of realizability, we can define pack learnability, right? So partial concept class H is pack learnable if there is a uniformly vanishing bound R of n and an algorithm alg, such that for every realizable distribution P, if the algorithm gets n IID points from P, then the expected error of the algorithm is bounded by this R of n bound. Right, so we can define learning. We can naturally express practical problems. But maybe a first question, a theoretical question we can ask is, are they really more expressive? Is it the case that with partial concept classes we can express learning, we can model learning tasks that cannot be expressed by total concept classes? In order to answer this question, we first need to introduce a definition which captures that. So the definition here is that we say that a partial concept class H is disambiguated by a total concept class H prime if every partial concept in H can be extended to a total concept in H prime, right? So for every partial concept in H, there is an extension in the big class, in the total class H prime. Notice that this means in particular that if you have a learning algorithm for H prime, then it will also learn H. So the question of are partial classes more expressive than total classes boils down to asking, is it the case that every learnable partial class can be disambiguated by a learnable total class? If the answer to this question is yes, then instead of modeling the learning task with H, we can just disambiguate it to H prime and model a richer learning task than the one modeled by H. Okay, so we answered this question. We say that we showed that the answer is no in a strong sense. So there exists a pack learnable partial class H, such that every H prime that disambiguates it has an unbounded VC dimension. And in particular, because VC dimension characterizes learnability of total classes, we have that H prime is not learnable. Okay, so there exists a partial concept class H that is learnable, and actually the learn rate is very, very fast, 1/n+1, such that any disambiguation of it has an unbounded VC dimension and hence is not learnable. It is interesting to know that the proof here hinges on a surprising connection with communication complexity and graph theory, and it really boils down to the recent breakthroughs by Goose, by Ben David, Khatami, Tal, and Goose, and by Balodis, Ben David, Goose, Jain, and Kotari. The last paper, by the way, appears in this conference. Okay. So we have this definition. We know that we can model more learning tasks. So now the fundamental question is which partial concept classes are learnable and how? Okay, so what we prove is that basically the same theorem that holds in the for total classes remains valid here. So any partial class H is pack learnable if and only if it has a finite VC dimension. And the VC dimension is defined in the same way as it is defined for total classes. So the VC dimension of a partial class H is the maximum integer D, such that there are D points in the domain. And when you restrict your class to these D points, you get to see all possible binary labeled patterns, all 2 to the D patterns. So in other words, we ignore the stars and we just consider the binary patterns. And if we see all of them, then this set is shattered, and the VC dimension is the size of the largest shattered set. Okay. Also, just like in the case for total classes, the optimal learning rate is the VC dimension over n. So when a class is back learnable, there is an algorithm that learns it, and the error decays like d over n. VC dimension over the number of examples. I should note that this strengthens a result by Phil Long from 20 years ago, who studied a related definition of learnability. So his definition was, or our definition is more restrictive. So it is harder to learn according to our definition. And another interesting point is that despite the fact that the theorem extends verbatim from the total case to the partial case, the proof is fundamentally different. In particular, uniform convergence does not apply here, and the empirical risk minimization does not work here. So the proof really is different. It's much more algorithmically. It's not just a reduction from generalization to optimization to empirical risk minimization. It's really more subtle. And this raises a very important question, is whether there are general principles in the spirit of empirical risk minimization that we have in the classical theory, which guide learning of partial concept classes, right? So great. We know that if the VC dimension is finite, then one can learn the partial class, but how do we do it? Is it just optimization? How is it done? So unfortunately, we don't have a satisfying answer for this question, at least not yet. But what we can show is that in a very strong sense, uniform convergence and ERM, which are the universal principles for total classes, are unable to explain learning of partial concept classes. And this is, by the way, very reminiscent of what is going on in practical machine learning. That again, we see that the classical principles, ERM, are unable to explain learning as it is done by deep neural networks. Okay, so let me elaborate on this a little bit. So maybe a first example is that the naive empirical risk minimization fails. So what do I mean by the naive by that? So consider the following class. So the domain is the numbers between 1 and n, and we have all possible functions f sub a, where a is a subset of the domain of size n over 2, and f sub a is 0 on every point in a, and it is undefined on every point outside a. Now this class has VC dimension 0, and it is indeed trivially learnable by the algorithm that outputs the all 0 function. However, if we insist of doing empirical risk minimization, if we insist on outputting an hypothesis from the class, a partial concept from the class that minimizes the empirical error, there is no chance we can learn so fast, right? Every algorithm which is restricted to use partial functions from H will require at least omega of n examples to guarantee error at most 1/4. And the intuitive reason is that any such algorithm will need to learn the support of the target function, and to learn the support of a distribution of support n over 2, of size n over 2, you will need the omega of n examples for that. However, if you allow to output concepts outside the class, such as the all 0 function, then you can learn it very fast with basically 0 error. Okay, but this is a very naive ERM, and we want to, I promised you that we answer this in a stronger, we give a negative result in a stronger sense. So is there a general reduction to empirical risk minimization? So maybe, right, so in the previous example, there was this disambiguating class H prime, which only contains the all 0 function, contains one function, and we can do ERM over H prime, and this also implies a learning algorithm for H. So the question here is it the case that for every learnable partial concept class, there is some total concept class H prime such that any empirical risk minimization for H prime, any ERM algorithm for H prime will successfully learn H. And notice that here I don't even demand that H prime will be learnable. All I want is to ask, can we reduce learning a partial concept class H to empirical risk minimization over a total concept class H prime? H prime need not be learnable. We really ask about empirical risk minimization here. This is the focus. And the answer that we show is no. So again, there exists a partial concept class with this dimension 1, such that for every H prime, there will be some bad ERM. There will be some ERM that with respect to H prime, which fails to pack learn H. And this is based on the same example from before, which is again based on these works in communication complexity and graph theory. Okay. Now let's consider another version of this question. So sure, maybe ERM doesn't work. Okay. But maybe it is still possible to learn every partial concept class H prime using another algorithm that is not necessarily an ERM, but still this algorithm outputs simple hypotheses from a learnable total class. Right? So in some sense, informally, you can think of it as how many parameters are needed to represent the output hypothesis while learning a partial concept class H. Right? If we can always output functions in a bounded class H, in a bounded total class H, so we need only a few parameters. And again, here we show that the answer is no. So, or you need many parameters. It will go to infinity. So again, there exists a very simple VC dimension, one-dimensional partial class, such that every algorithm A that learns it has range with unbounded VC dimension, right? So if you look at all the hypotheses that the algorithm might output, it necessarily has an unbounded VC dimension, right? The complexity of the output hypothesis necessarily grows with the number of examples. Okay, so let me summarize. So indeed, progress in practical machine learning poses major challenges to theory. And as a result, there is significant effort in rethinking the theory, which is great and healthy, and that's what we do here also. However, I want to say that I think one conclusion from this work is that one should not discard or cancel the classical theories. And indeed, as we saw here, natural modifications of the axioms and the definitions, right? So here we just allowed using partial concepts rather than only total concept. So such very simple modifications lead to more realistic models, and we still retain the mathematical elegance and at least some of the wisdom that was accumulated by the classical theory. Yeah, and that's it. Thank you very much for listening, and I hope to see you in the poster session, where I'll be happy to discuss the proofs in more detail. Thank you very much, and bye-bye.